Okay, today we're going to start a new topic, which is brute force search, a very important idea. And there's actually three things that I'm hoping you're going to get out of today. The first is a practical skill, which is just how to use some nested for loops to loop over data, and in particular to systematically list all of the possible combinations for something. And then another is this big idea, which is brute force search. And that idea is that you can think about any problem at all as a search problem. It's just the problem of searching through all of the possible answers and testing each one to find the actual answer. And last, there's some vocabulary, the idea of a search space, the idea of brute force search, and something called the curse of dimensionality. And some of these ideas are going to get built upon later when we talk about machine learning, and they're kind of like important ideas in the heart of machine learning. All right, so let's do a quick warm-up by reviewing a familiar idea. So if you're searching through a list to find the largest thing or the smallest thing, you know how to do this. It looks like this. But I want to show you three variations, and you can sort of pay attention to what's different in the code of the three variations. So if I've got a list of things and I want to find the largest, I can initialize a variable called largest so far as the first item, and then I can loop over all the other items and I can check the size of each one to see if it's larger than the size of the biggest one so far. And so it looks like this. So I can move and I check it, and I move and I check it, and let's pretend this one is actually larger. If it's larger, the if statement's true, and so I take that one and save it into my variable as the new largest so far. And then I go through, and then when I get to the end, by the time I get to the end of the list, I'm sure that the item in my variable is actually the largest. Okay, so here's a slight variation. Take a look at the code and see if you can identify what's different about it. So this is exactly the same. I'm still initializing largest so far and comparing each item's size to that thing. The only difference is I'm saving two things. I'm saving the actual thing that's the biggest thing, and I'm saving a number that represents its size. So for example, if this was a list of products and we were going to try and find the most expensive product, largest so far would be an actual product object, but then largest size would be the price of the product. So by saving them separately, what you can do is it makes it just a hair faster, especially if it's very slow to calculate the size of each item. If you look at the previous version of the code, if the first thing is the largest so far, as I'm looping through all of the other things, I'm recalculating the size of the largest so far over and over and over again. But there's no real reason to do that because it's not changing at all. So that is a little bit slow. So this variation lets you only calculate the size of each object once, stored in variables, and then you don't recalculate the size unless you have to because you've moved on to a different item. So if we're going to run this, item 0 has size of 17, and we'll compare it, and we'll compare it, and we'll compare it, and then in our imagination, this is the one that's larger, and so we save two things. We save the object, and we save its larger size, which was 25. Okay, this last variation has more minimal code. Here, instead of storing the actual object itself, we just store the location of the largest thing in the list. And the rest of it's the same. So inside code, we just get the item out of the list corresponding to the largest location, and we get the item out of the list corresponding to the next one we're going to check, and we compute the size of both. And in this case, we store when we... Oops, sorry about that. And in this case, the thing that we store when we find the largest is not the item at all, but just the index. Index 3 corresponds to the new largest. Okay, so that's a warm-up, just to show you that there's several variations. So what if we have a whole bunch of data and we want to find the closest match for some target item that we have? This kind of problem appears in a lot of different circumstances. So a very generic one would be we have a whole bunch of points in space and we've got a target point, say at 1232, and we want to loop over the existing points and find which one is closest to our target point. This same idea appears in a lot of different ways though. So it could be a list of people and I want to loop over and find the person most similar to a target person. And it could be that this is like a dating website and we're trying to find compatibility for matching, or it could be that these are customers for our website and we want to find a customer that's similar to our target customer so that we can make recommendations to the customer based on ratings that another customer has given. So for this version of the problem, it's pretty clear how this is a variation of the previous idea. What we'll do is we'll loop over every single point in the list, and we'll calculate the distance between our target point and the new point, and we'll keep a variable that stores the smallest distance we've found so far. And every time we find a new smallest distance, we'll remember the point that corresponded to that smallest distance, and by the time we get to the end of the list, that will be the point that's closest. But what about this one? This one, we're talking about people and similarity. So how is that the same? What we need is we need to introduce a similarity measure, and that would be like a method that takes two people as input and returns some number that ranks their similarity. And there's a lot of ways that you can do that, but typically this is based on data that we have about the people. So you could imagine that maybe higher numbers represent greater similarity. In actual practice, usually it's lower numbers that represent greater similarity, but we'll talk more about kind of why that makes sense in a second. But the point is, once we have a way of attaching a number to similarity, then the approach is exactly the same. We loop over all the people. We use the method to give us a number for the similarity between each pair, and then we find the pair that has the smallest number. Or I guess if more similar is a higher number, then we'd find the pair with the highest number. And this idea of finding the closest match as finding the most similar item can be extended to other areas as well. So if we want to recommend based on movies, we could find which movie is most similar to an existing movie that a customer likes in order to recommend a new one to them. I just thought of another one for people. What if these are all senators, and Senator P is our favorite senator, and we want to know which senator is most similar in voting record to the senator that we like? You know, that's a question that we might ask. Or we might ask which senator is the polar opposite of the senator that we like. And so these are all questions about trying to find things that are similar or dissimilar. And as I suggested, the overall pattern is pretty much the exact same thing as the warm-ups that we were looking at. We loop over all the things, calculate the similarity, and if the similarity is a better score, we save it as the new best score. All right, so in all of those examples, we were looping over a list to find one thing. What if we're looking for pairs of things or trios of things? What if we're looking for larger numbers? So this is the practical skill that I talked about of using nested loops. So back to the kind of not very interesting example, we've got this same list of points, but this time I want to know which 2 points in the list are closest to each other. So you might imagine a solution that looks something like this. We'll save a pair of points, and at the beginning we'll initialize them to null, and then the best distance will be the smallest distance we've ever seen so far. And the idea is we'll loop a pointer I over all of the points in the list. We'll loop a pointer j over all the points in the list. And so then for every pair of them, we'll get the distance between the pair and say, is that a better distance than the best one we've seen so far? And if the answer is yes, then we'll save both points and we'll save that distance as the best distance. So this code has a number of problems with it. Pause the video for a second and see if you can identify what they might be. Okay, so the first problem is it doesn't really make sense to initialize best distance to 0 if the thing we're looking for is the closest pair of points. Because we only save points and update the best distance if we find a distance that's smaller than the best distance. But it's not possible to find a distance that's smaller than 0. So it's like this code will loop through everything, but it will never update because we've initialized best distance already as the smallest possible. That might seem like a ridiculous error to make, but trust me, students and professional programmers make this kind of initialization mistake all the time because it's easy not to think about it. It's easy to say, oh, this just needs to default to 0 and then it'll get replaced later on. So you really need to think hard about what makes sense as a good value to initialize something to. There's kind of 2 classic solutions to this problem. If I'm trying to find a minimum, such as a minimum distance, you can initialize your best distance so far as the largest number possible. In this case, double.max value. And that makes sense because right away, the first time through the loop, the first distance we calculate is guaranteed to be smaller than that. So you'll replace all of your variables on the first thing that you hit through the list. A different variation would be assign your 2 points to be the literal first 2 points in the list, and then calculate the distance between them, and that will be your initial closest distance. And then it's very unlikely that the first 2 you choose is actually going to represent the closest pair, so then that will get replaced later on as you loop over all the rest of the pairs. Okay, big problem number 2. We don't actually want I and j to loop over everything. In particular, we don't want I and j to be the same value, because that would then ask what's the distance between a point and itself, and that would be 0. And so at the end of this code, we would say, hey, we found the closest pair of points, and that pair is point 0 and point 0. But that's not really a pair of points. So we need a way of enforcing that point 1 is actually different than point 2. There's actually a second problem with this, which is even if we put it in an if statement to say only do this inside if I doesn't equal j, that takes care of the previous problem. But the new problem is this would test each pair of points twice. So imagine the pair of points, point 1 and point 3 here. We'd test it once when I equals 1 and j equals 3. But then we test that same pair another time when j equals 1 and I equals 3. Because each index here is looping over, each pointer here is looping over all of the indices. So a good way to solve both problems at once is not using if statements on the inside. It would be to enforce that the second point has to come after the first point in the list. And we do that by initializing j to be I plus 1, the location after I for whichever point I we've gotten out of the list. So that's the kind of classic solution to this set of problems. So then what this would look like to execute is I initializes to 0 and j initializes to 1. And then while I is 0, j loops over all the other things. And then once j is done with its loop, I increments to 1, and j initializes to the one after, 2, and loops over all the things. And then I increments, and j loops over all the things in front of it, and so on until eventually we get to the end of the list. And that process guarantees that we visit every pair of items in the list exactly once. Okay, so what if we want 3 things out of the list? You can probably imagine what this is going to look like. So let's pretend I want to find which 3 points make a triangle whose area is greater than 100, but I want, of all of the triangles whose areas are greater than 100, I want to find the smallest one of those. So we'd have 3 pointers. We'd have an I, a j, and a k, because we know we need 3 different points. And they'd all range over all the values, except we'd enforce that j is always larger than I, and k is always larger than j. And that guarantees we're going to visit all triples, but each one we're only going to visit once. And then the rest of the pattern is more or less the same. We'd calculate the area for those 3 triangles, for the triangle formed by those 3 points. And if the area is larger than 100, then we'll test if it's the smallest we've seen so far. And if it is, then we'll save things. So let's hit one more big, important practical example before we turn to brute force search proper. And that idea is A/B testing. You might have heard of this. The idea of A/B testing is you're going to compare the performance of different versions of something to find the best one. And this is most commonly used in websites where you want a customer to click through, or in this case, the Obama campaign in 2008 was the first political campaign to really use this idea. And in that case, they were trying to get as many people as possible to give them their email address to receive information. So what is this A/B testing? This is what the web page looked like, or this is one version of what their splash page looks like. But this sign up button could have different possible text. It could say join us now, or learn more, or sign up now, or sign up. It might not seem like those are that different from each other, but actually the text that you choose, the color you choose, the media that you have here can all make a large difference for whether someone decides to press that button or not. Netflix does a whole lot of this and has written a lot of really interesting stuff about how they collect data and how they use data to modify what their landing page looks like and like what their selection pages look like. So in the particular article that I read, which you can find in the speaker notes on the slide, they were testing kind of two things, and each thing had several options. So there was the text on the button, which I already read, and then there's the graphic, the media that displays next to it. So they had a picture of a family, and then they had a picture that was supposed to indicate the concept of change. They had a video of Barack Obama speaking, and they had a couple of other videos with other content. So, here, let's go back one slide, actually. So they had, let's see, 4 different options for the button text, and they had 6 different options for the media. So that gives 24 combinations overall if you're going to choose one button text and one media. And what they did is each person who came to the website, they gave them a particular combination of a button text and media. And then they tested to see did the person click through or not. And they collected all of this data, and they found that some combinations performed much better than others. In other words, some combinations, people were much more likely to click through than others. So how big a deal is this? I'm going to read you now some text from the article where this graphic came from. The winning variation had a sign-up rate of 11.6%, which you can see right there. The combination that they were going to use just based on what people in the campaign liked, people in the campaign said, this graphic seems like the best to me. That only had a sign-up rate of 8.26%. So because they used the combination that was based on the testing, that was a 40.6% improvement in sign-up rates. So what does that actually mean in terms of actual numbers? Over the course of the campaign, 10 million people signed up on this splash page. And that was the splash page using their kind of tested best combination. If they hadn't run the test, if they'd just gone with what the campaign originally thought was good, they would have only had about 7.1 million, not 10 million. So that's a difference of 2.8 million email addresses. On average, each email address they collected donated an average of $21 over the course of the campaign. And so based on averages, those 2.8 million email addresses make a difference of $60 million in donations. So think about that. The campaign had some favorite graphics, they had some favorite text, but instead of just going with their gut feeling about what was best, they ran some tests, which were pretty easy to run. And based on those tests, they got $60 million more than they would have in donations. So that's why companies do this kind of stuff. It can make huge differences if you have lots and lots of people visiting a site. Okay, so what does this all have to do with code? Let's imagine, and this is not super accurate, but I think it conveys the general structure of the idea. Let's imagine that each time someone comes to a web page, there's a method that returns the contents of the web page. It's called getWebPage. So if we wanted to serve people different combinations of the button text and the media, we could have 2 arrays, an array consisting of all possible button texts and another array consisting of objects that represent images and movies. So that's the media. So what we need to do is we need a list of all of the possible combinations of these 2 things. And then when someone comes to the web page, we'll select a random one from the list and use that to fill in the details of the web page. So to do this, you'll create a data transfer object. You could call it page test, for example. Although it looks like down here I've just called it test. And so the fields for your object are just going to be the different things, or the different items that you're going to choose different options for. So for us, it was just text and media. And so then we'll have a method called generate all combinations that take the 2 arrays as input and give back an array list that consists of objects representing each of the possible combinations. So we finally arrived back at looping. You can create an array list. You can loop over each location in the text array. You can loop over each location in the media array. And then you can create a new object consisting of that text and that media. And then you add that, and so put together, that represents a particular combination. And then you add that object to your array list, and then at the end you return it. And now you've generated an array list of all the possible combinations. Okay, we're going to cut the video here, and then in the next video, we'll look at how all problems can be viewed as search problems, and that's what brute force search is more properly.